A set is a collection of well-defined and distinct objects. Well-defined means that the criteria whether to include which elements in the set or which not to include in the set should be very clear, and all the elements should be different. We cannot have two same elements in a set. Examples of infinite sets. There are two kinds of sets, finite sets and infinite sets. Infinite sets are the sets which contain an uncountable infinite number of elements which we cannot count. There are so many in number. For example, set of natural numbers. These were the first number that man discovered for counting in daily life. They start from 1, 2, 3, 4, and so on. The dots indicate that the sequence of numbers does not end at 5. After 5, you have 6, 7, 8, and so on. There are millions and billions of numbers in the set. Similarly, if you add 0 to natural numbers, you get the set of whole numbers. So, whole numbers are 0, 1, 2, 3, and so on. And if you take the negative of natural numbers and combine them with whole numbers, you get a set of integers. So, set of integers contains 0, plus, minus 1, plus, minus 2, and so on. Plus, minus 1 means there is plus 1 and minus 1 both. We can write the set by writing the negative integers first, then 0 and the positive integers. So, we can write the set also like this. And then we have set of odd numbers. Odd numbers are the numbers which are not divisible by 2, which do not divide upon 2. So 1, 3, 5, 7, 9, and so on. These are the odd numbers. And then we have set of even numbers. These are the numbers which divide upon the table of 2, 2, 4, 6, 8, and so on. These are the set of even numbers. Again, this is also an infinite set because it doesn't end at 10. The numbers continue like 10, 12, 14, 16, etc. Next, we have the set of prime numbers. Prime numbers are those numbers which do not divide on any table except 1 or itself. Uh, they have only two factors, 1 and itself. So 2 is the smallest prime number, then we have 3, 5, 7, 11, and so on. 2 is the only prime number which is even as well. Then we have set of negative integers. Negative integers are the negative natural numbers simply. Alright. Next we will consider finite sets. Finite sets are those sets which contain limited number of elements. That is, they are countable and they are not infinite. There are not too many that we cannot count. For example, set of first 6 even numbers. These are just 6 even numbers, so this is also a finite set. And we denote the number of elements in a set by, for example, if this set is denoted by A, n bracket A means number of elements in set A, and which is 6. And it is also called the cardinality of the set. The number of elements in a set is called the cardinality of that set. So cardinality of the set A is 6, since it contains 6 elements. This E-type symbol, which is actually a Greek letter epsilon, is used to denote whether that an element or object belongs to a set. So we read it as is an element of. Is an element of. We read it as, and how do we write it? The symbol epsilon denotes is an element of. So for example, if you write 2 epsilon A, that means we will read it as 2 epsilon A denotes that 2 is an element of the set A. So in normal practice, we read it as 2 is an element of set A. Similarly, since 8 is also in the set A, 8 is an element of set A, right? Consider any number that is not in the set A. For example, 7. So how will write? We will put a slash over this symbol to denote that this element does not belong to set A. So 7 slash epsilon means 7 does not belong to A. 7 is not an element of A, right? Similarly, we can state any other number. For example, 100. 100 is not an element of set A, like this. Now, examples of finite sets. Example, set of vowels of English alphabets. As you know, there are only 5 vowels in the English alphabets, A, E, I, O, U. So this set contains how many elements? We can write it like this. N bracket B means number of elements set in set B is 5, and that means the cardinality of the set is also 5. Set of factors of 42. How can we find the set factors of 42? You can write 42 as 1 into 42, or 2 into 21, 3 into 14, 6 into 7. This way we have got all the factors starting from 1 and ending at 42. So we can put them in a set, which will be the set of factors of 42. We are calling the set C. And how many elements are in this set? You can count them. Number of elements set is 8. For example, set of multiples of 4 less than 40. Multiples of 4 or any number obtained by multiplying that number by 1, 2, 3, 4, etc. So multiples of 4 would be 4, 8, 12, 16 till we are less than 40. So 36 is the last multiple, because after that the numbers will be 40 or more than 40. The multiples will be more than 40. So how many elements are in this set? There are 9 elements in this set. Set of perfect squares less than 50. Perfect squares are the numbers which can be written as the square of some number. For example, 1 can be written as square of 1, 4 can be written as square of 2. So 4 is a perfect square. Similarly, 3 is not a perfect square. Similarly, 9 can be written as square of 3. So 9 is a perfect square, not 3. And similarly, 100 can be written as a square of 10. So 100 is a perfect square, but 10 is not a perfect square. So these are the perfect square which are less than 50. And how many these numbers are, you can count them. Number of elements in set E is 7. So this is also the cardinality of set E. Set of prime numbers less than 2. Prime numbers less than 2, we don't have any prime number less than 2. So this is going to be an empty set. We simply put nothing in between the brackets. That will denote an empty set, and it also called as a null set. We have another notation to express an empty set. F is equal to, this symbol is read as phi, so that the number of elements in the set F is 0. Another empty set of polar bears living in the Sahara Desert. Sahara Desert is a hot desert. There is no polar bear there, so this is also an empty set. So we can say that the number of elements in the set is 0. 0 is not the element, but the number of elements in the set is 0. So note that if you write a set H is equal to, in the bracket if you write 0, it doesn't mean that it is an empty set, because it contains a number 0. 0 is an element, so the number of elements in the set H in this example is just 1. So far we have discussed the listing method of sets by just listing the elements between two brackets and putting commas in between the elements. There is another powerful method of expressing a set or writing a set, which is called set builder notation, and we will discuss this notation through examples. Question number 1, write the following sets in the set builder notation form. So we are given a set in which its 5 elements have been listed by putting commas in between those elements. In set builder notation, we describe a set by the nature of the elements, right? So how that set is constructed, that is used in the set builder notation. So these letters, as you can see, are the vowels of English alphabet. So we will express the set like this. So we will write the name of the set and put the same curly brackets, and X will denote each X. Set A consists of elements X such that these two dots are read as such that. So this first X is read as elements X. Such A is a set of elements X, then such that these two dots or column is read as such that each element X is a vowel of the English alphabets. Alright, such that each element X is a vowel of English alphabets. And we read it as completely, A is a set of elements such that each X is a vowel of English alphabet. Okay, now second example, uh, we have a set B starts from 2, 4, 6 and so on. That means it's an infinite set. And if you watch them closely, these are the even numbers starting from 2, 4, 6, and these are all the even numbers. There is no limit from where they are starting, where they are ending. They're starting from beginning and they are ending nowhere. So we can write set B is a set of elements X such that X is an even number. Third example, set C, in which the numbers are starting from 12 and then 14, 16 until 20 we have. If we watch them closely, these are even numbers and they're starting from 12 and ending in 20. So we will mention these two things, that these are even numbers and they're starting from 12 and ending at 20. So we can write that set C is a set of elements X such that X is an even number, and that x is between 12 and 20. These lines below inequalities show that 12 and 20 are also inclusive. They are also included. If we leave those lines, we just write the inequality, that will mean 12 and 20 are not inclusive. Third example, D. These are the numbers 31, 33. We can easily identify them as odd numbers, starting from 31 and 39. So we can write set D is a set of elements x such that x is an odd number and x is between 30 and 40. Now this time I have not used lines below the inequalities. That means 30 and 40 are not inclusive. But all the numbers between 30 and 40 are inclusive and they are odd numbers. We have already stated that they are odd numbers. So between 30 and 40, you have the odd numbers 31, 33, 35, 37, 39. Fifth example, we have a set E, and if you watch the elements of see the elements of set E, they are neither all even, neither they are all odd. But if you watch them closely, and they are the squares, they are the perfect squares, and they are not all the perfect squares. This is not an infinite set. This is a finite set. And how can we define them then? First, I think we have noticed that these are the perfect squares. So let's write set E is a set of elements x such that x is a perfect square less than 50, because you can see that all of them are less than 50. No perfect square is more than 50, and they are starting from beginning, and no number is missing from beginning till uh, numbers less than 50. Okay, now the sixth example, f minus 10 dot 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 means, and then minus 3. This means the numbers between minus 10 minus 3, which are minus 9 minus 8 minus 7, they are also inclusive. Then you have 0 1 2 3 and then dot dot dot. That means the numbers between 3 and 10, 4 5 6 7 8 9, they're also inclusive. So if we watch them closely, these are the integers, and they start from minus 10 and end at 10, and there is nothing missing in between. So we can say that set F is a set of elements x such that x is an integer and x is between minus 10 and 10 inclusive. Seventh example, set G, which has only one element 0. You can define this set in many ways. You can not simply write that set G contains an element 0. No, that will not be a proper way of expressing. You have to expressing the set. You have to apply some criteria so that you get the result 0, only one element 0. So one way of doing this is that we can say that set G is a set of elements x such that x is an integer and x is between minus 1 and 1. You can verify that there is only one integer between minus 1 and 1, and that is 0. So this definition is correct for this given set. Number 8 example, we have a set H which has nothing in between the braces. That means it's an empty set. How can we define an empty set? We have to apply criteria which results in no elements, right? And there can be more than one criteria. So let us define one of them. Set H is a set of elements x such that x is an odd number less than 1. So there is since there is no element odd number less than 1, there can be no element in this set H. So H becomes an empty set according to this criteria. Ninth example, set I has only two elements minus 4 and 4. Now how will you set up criteria for this? You can say that I is a set of elements of x such that x is an integer whose square is 16, because the square of minus 4 is 16, minus 4 into minus 4 is plus 16, and then again square of 4 is also 16. So we can say x the element x in set I is a number whose square is 16. Or there is another criteria. You can write set implementation for this on another criteria, that set I is a set of elements x such that x is an integer and such that this integer's square root, this is an integer whose square root which is equal to the square root of 16. Now square root of 16 are 2, negative 4 and 4. So this criteria also fulfills the requirement that we have the square roots of 16 in the set I, which are 2, minus 1 and minus 4 and plus 4. Okay, question number 2 says list all the elements of the following sets in set notation. Uh, we will simply list the elements in the following sets. So first set is given in set builder notation. We will list all the elements, which is the normal or the regular notation, the easiest one. It says that set A is a set of elements x such that x belongs to a set of whole numbers and x is less than or equal to 10. That means we have to list all the whole numbers which are less than or equal to 10. The whole numbers start from 0 and then they are like 0, 1, 2, 3, and we'll write all the whole numbers from 0 to 10. It's a finite set containing only 11 elements. Second example, in this set we have been given a set B. B is a set of elements x such that x belongs to a set of whole numbers and x is between -5 and 2. There are no lines below the inequalities. That means -5 and 2 are not inclusive, but all the integers between -5 and 2 are inclusive. On the number line, you can imagine that next to -5, on the right side of -5, you have -4. Then again, on the right of -4, you have -3. So the numbers from -4, -3, -2 till 1, because 1 is less than 2, we will not include 2. These numbers fall in this set B, so we will write all these elements of set B. The third example we have set C is a set of elements x such that x is a positive integer divisible by 8. Integers divisible by 8 means are those numbers which can be divided by 8 completely. They are also called the multiples of 8. So there is no limit how many multiples or up to which number of multiples. So we will write all the multiples of 8, writing only first few and then putting dot 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 to indicate that they continue like this. So set C is equal to 8, 6, 24, 16, 24, 32. These are all the multiples of 8 and they continue like that. This is an infinite set. Fourth example, D is a set of elements x such that x is a prime number which is a divisor of 42. So there should be two things that x should possess. It should be a prime number and it also should be a divisor or factor of 42. Divisor is another word for factor. So we did find the factors of 42 in a previous discussion. We will choose the prime numbers from those factors, the prime factors of 42. So 2, 3, 7 are only the prime factors of 42. 6 is not a prime number. Similarly, 21 or 14 are not prime numbers. So next example says set E is a set of elements x such that x is a two-digit number such that sum of the digits is 8. So we have to see two-digit numbers whose sum of the digits is 8. How do we obtain the sum of the digits? We simply add the two digits. For example, in 21 the sum of the digits it's 3, but we have in this set there are only those elements or numbers included which have the sum of the digits equal to 8. So if you start from the minimum first digit and the maximum second digit, minimum first digit can be 0 and the second can be 8, but 0 is a single digit number. So next we take 1 as a first digit and second digit can be taken then 7. So 17 is the first number and then 26 or 26 is the second number. So like that we can write all the numbers which have the sum of the digits is equal to 8. 80 will also come because it's a two digit number, but 08 will not come because it becomes a single digit number. Sixth example, set F is a set of elements x such that x is equal to 5p. And now this is a little different kind of set and Miller notation in which another variable p has been used. So read it carefully. Set F is a set of elements x such that x is equal to 5p. And what is p? P is defining p belongs to set of whole numbers. P is an element of set of whole numbers and p is less than or equal to 4. So all the values of p, that is all the whole numbers which are less than or equal to 4, they are 0, 1, 2, 3, 4. We can take those values of p and we'll put those values of p in place of p in the equation x is equal to 5p and we'll get the values of x. For example, when you put 0, 5 into 0 will be 0. Next, you will put p is equal to 1. So 5 into 1 will be 5. So similarly, you can get the values of x. Last value of p is 4 because p is less than or equal to 4. When you put p is equal to 4 in x is equal to 5 is equal to x is equal to 5p, then 5 equal to 4, it will be 20. So the last element will be for 20. So we'll write all these elements starting from 0, 5, 10, 15 and 20. This is a finite set containing 5 elements. Next we have seventh example. Set G is set of elements x such that x is a square. So what is a? A belongs to a set of natural numbers and a is between 2 and 6. That means you have to pick a natural number between 2 and 6 and you have to take its square. That will be the element of set G. Okay, for example, more than 2 you have 3, greater than 2 you have 3. So take the square of 3. 3 square of 3 will be 9. So it will be the first element of G. Then next to 3 you have 4. That means you will take the square of 4. X is equal to a square. So 4 square, it will be 16. So next element is 16. So 9, 16 and so on. We will take the square of 5 also, which is 25. We'll write all these elements: 9, 16 and 25. Next, in part 8, the eighth example, we have H is a set of elements X, such that X is a natural number, X belongs to the set of natural numbers, and 3x minus 5 is equal to 5. 3x minus 1 equal to 5. This is an equation we have to solve, and X is a natural number. X should come out to be a natural number. So let's solve this equation. 3x minus 5 is equal to 1 is equal to 5. Minus 1 will go to right hand side, it will become positive. So that we will have 5 plus 1 on the right hand side. 5 plus 1 will be added, it will become 6 on the right hand side. Then 3 will divide on the right hand side, then 6 will be cancelled by 3. We will have 2. 2 is a natural number. So we have only one element fulfilling the given criteria, and that is 2. So we will write here X is equal to 2. And then we have next example 9. Set I is a natural number whose square is 36. We have to write all the natural numbers whose square is 36. All right. So for example, if a square is less than 36, not 36. For example, if you take the square of 1, its square is less than 36, we will write 1 in the set of natural number in this set I. Similarly, if you take next natural number 2, then its square is 4, that is less than 36. Similarly, we will keep on writing the squares of natural numbers till the value of the square is less than 36. So we will write all these numbers, because till 5 you have the square value of the square less than 36. After 5 you will have 6. The square of 6 will be 36, which is not less than 36. So these are the only elements which belong to the set I. 10th example, J, the set of even numbers divisible by 5. So we can write a set of even numbers divisible by 5. For example, 10 is divisible by 5, it is an even number. Next we have 20, which is even number and divisible by 5. So we will write all the even numbers which are divisible by 5. They are in fact the multiples of 10. Okay, number 11 example, set K is a set of element X such that X is a natural numbers and X is between 5 and 6. So we have to write all the natural numbers which are between 5 and 6. Since there is no natural number between 5 and 6, we have 5.5, 5.3, etc., but they are not natural numbers. They are numbers but not natural numbers. So since there is no natural numbers between 5 and 6, there can be no element in set K. So K is an empty set. In 12th example, we have a set L, which belongs to a set of real numbers. Real numbers are all the numbers which can be decimals, fractions, or integers, positive integers, negatives, all those numbers. And what does the criteria say? Set Wilder form says that set L is a set of elements X such that X belongs to a set of real number, and the square of real number is -1. There is no real number whose square is -1, because after taking the square, even a negative number becomes positive. So again, there is no real number fulfilling this criteria. That means there is no element in set L. So this is an empty set. Another example, number 13, we have a set M in which X is a prime number, and the prime number is between 45 and 50. That means we have to list all the prime numbers between 45 and 50. So we will see how many prime numbers, which are the prime numbers between 45 and 50. So after 45 we have the number 46, 47, 48, 49, out of which only 47 is a prime number. So M contains only one element, 47. Equal sets. Two sets are said to be equal sets if they contain exactly the same elements. The number of elements is the same, and the elements should also be exactly the same. Okay, let us consider an example in which we have a set A in which we have 5 elements, 5 letters E, A, R, T, H. B also has 5 elements, H, E, R, T, H, E, A, R, T, and C has only one element. These are not 5 because it's a single word. And D also has only one element, Earth. It's also a single word. Set E has 3 elements, BSU. Set F has USB. So you can identify which two sets are equal. So we can easily see that set A and B are equal and sets E and F are equal. C and D are not equal, although they contain one element, but their elements are different. C contains heart and D contains earth. So they are different, although they contain one element. So only set A, B are equal, and set E and F are equal to each other.